Right, it seems like we have our audience. So as I said before, I'm Dominic DeCanio. I'm joining with Megan Anderson as the software demo days point of contact in the primer team. And we're happy to present today demo days with WecOptTool. Swara, would you like to get on the line and say a few words?
Yeah, everyone, thank you so much for making it to another software demo day. And yeah, we today are focusing on WecOptTool, a Sandia developed tool. It's an open source software for, very sorry, before I say that, yeah, if y'all have been here before, you know, here at Software Demo Days, we aim to increase cross collaboration between marine energy software developers and just get the ideas rolling on what more innovation can be made in the marine energy software space. And today we're focusing on WecOptTool, which is a Sandia open source software for conducting optimization studies of wave energy converters and their control strategies. And thus it allows users to work much more efficiently. It solves the entire timeline of wave patterns, how much energy they're producing, as well as their shape, direction, and other aspects, all to make your WECs as efficient as possible. And yeah, I'm just so excited to learn more about it today.
Thanks so much, Swara. Just a reminder that this demo day will be using CoCalc. So if you're having trouble with your CoCalc or there's any technical issues, you can just throw them in the chat of the meeting, and then the other people on the team will be able to help assist you. And with that, I'd like to turn it over to Carlos, and you can take it away for the demonstration.
All right, thank you. Let me share my screen. Can you all see the title slide? Cool. So WecOptTool is a tool for control co-design of wave energy converters and uses the pseudo-spectral method. But don't let the word spectral fool you. It's a time domain solver, so you can completely handle nonlinear dynamics. So just a quick overview. I'll talk a little bit about control co-design and the pseudo-spectral method and why we would want to do that. Then very briefly about the WecOptTool, the structure of the code and how you use it. And then we'll go right into a demo and then Q&A. So the idea behind control co-design is that the WEC dynamics has many parts of the dynamics are very tied together, they depend on each other. You really can't simulate one alone. So the effects of your controller, your load, will have an effect on how your buoy moves and vice versa. It's highly coupled dynamics from the buoy all the way through your generator and your controller. And you really shouldn't be looking at it individually or sequentially. And we'll talk a little bit more about that, but just as an idea of all the systems involved in modeling a WEC, we started with the waves and the hull itself, so the hydrodynamics, wave structure interactions. But then we transfer that power into the drivetrain, which has its own dynamics. It can have its inertia, stiffness, friction losses, and then that fits into the generator, which again has its own dynamic that convert that rotational motion into electricity. And then furthermore, we can control the load. And so you can think about it as controlling the torque on the generator, for example. And all of these are highly coupled. You really cannot just model the wave structure interactions first and then design your PTO. They all depend on each other. That's a key idea behind control co-design, is that you have to look at all the systems together because the dynamics are so highly coupled. So one way we like to visualize it is if you first optimize your geometry and PTO based, say, on transferring the most mechanical power from the wave into your PTO, you might come up with a design optimal design here. And then you might want to find the best controller for this device, and you come up with this optimal design right here. But it is very likely suboptimal because you left all of this space unexplored. And the idea being that because the dynamics are so highly coupled, the optimal solution cannot be arrived at sequentially by first optimizing power flow into the mechanical systems, for example, and then into the generator and then the controller. And this is how we used to think about it when the control project started, and the idea was, how can we best control a WEC to produce the most power? And that ended up being the wrong answer. Once the WEC is designed, there's very little the controller can do. You really want to be looking at designing the controller and the device simultaneously. So this is another way that we show this when we're presenting. So we say that all the WEC subsystems contain relevant and interacting dynamics. And there's very little a high-performing controller can do compared to the benefits of truly aligning the wave, whole, PTO, and controller. And we won't go into it today, but using linear theory, we can show very nicely how this is a two-port impedance matching problem. So you really want to match the impedances all the way from input to output along your power conversion chain. And you get the most gain by matching those impedances, which can only be done by designing controller and WEC and PTO together as a whole system. So in this diagram, on the left, we have ocean waves, and on the right, we have usable power. And in light blue, we show the system that we designed first and it's fixed, and the systems that we optimize. And the way we used to do it was we designed the whole buoy first, and we will try to make it like resonate with the waves or convert the most power, absorb the most power from the wave. And then we will try to optimize the controller. Later on, we started modeling the actual PTOs. In WECSIM, you can think of like PTO sim, for example. So we started modeling the dynamics of PTOs, but we were still designing PTOs first and then trying to get the controller to do some magic and make the WEC produce a lot of power. What we've been doing now with control co-design is we've been designing the PTO and the controller together and optimizing them together. So we start from some WEC geometry, and we optimize and we design the PTO and controller together through co-optimization. And the end goal, the ideal, will be to consider even the geometry, everything together. And yeah, this is how we used to do it, and it's pretty bad. This is an improvement, and this too is what we call control co-design. It's when we're optimizing physical designs of the device and the controller simultaneously. Now, I mentioned we use the pseudospectral method. So what is the pseudospectral method? First, and I'll repeat it again, it is in the time domain. It's a time domain solver. It's helpful to start with the left side, a time-stepping initial value problem. I think most of us are familiar with those. It's, for example, how Simulink and WECSIMs solve the problem. You start with a known condition, and then you take a small step in time and find the next state of your device, and so on. In the pseudospectral method, because it's an optimization tool, we frame the problem as an optimization problem where we're trying to maximize the power production. And then the dynamics at the different time steps, we can think of this as position or velocity, are left as free variables to be optimized. But then we include the dynamic equation as a constraint. So initially, we randomly initialize the values of your velocity or your position, and then the optimizer converges to a solution that maximizes your power production and satisfies those conditions. So this is the problem formulation. We're minimizing some function j, in this case, maximize power, of your state x, such that the dynamics are respected. So we put a condition where r of x equals 0, and r is your dynamics in residual form. And we'll talk about that in the next slide, I believe. And then this is also very powerful. We can add any number of arbitrary constraints, either equality constraints or inequality constraints. And in this case, our state vector x, our optimization vector x, is includes both the dynamics and the controller or whatever you're optimizing. So the dynamics will be the position of your WEC at every time step. So if you have 200 time steps, that's your dynamic state is 200. And in the pseudospectral method, we don't do, it's called pseudospectral because even though it's a time domain solution, we represent the time series with their Fourier coefficients. So really, this x here is the Fourier coefficients of your time trajectory, your position trajectory. And in this framework, we can find the optimal trajectory of position, velocity, and controller simultaneously and satisfy all the dynamics equations. So how do we write the dynamics equation as a constraint to an optimization? Well, we can start from the typical mass times acceleration equals sum of forces, your inertia equals your sum of forces. And then we can write the residual form of this equation, which it's equal to 0. And provide this as an equality constraint to the optimizer. In our case of a typical WEC, we have inertia, we have radiation forces, hydrostatic forces, excitation, and then any number of additional forces. And this is the formulation we use in WecOptTool, where by default, and you can change this, but by default, the dynamic equations includes inertia, radiation, hydrostatic, and excitation, and the user can provide additional forces. And then one last thing about the pseudospectral method, it's an optimization, and we do gradient-based optimization, which means we need the gradient of our cost function, for example, power, with respect to our inputs, which are the hundreds of variables that represent our position trajectory and our controller trajectory. So these are high dimensional gradients in order to do gradient-based optimization. If we were to do finite difference, we would have to evaluate our function, our power production at hundreds of cases just to get the gradient at one point, because finite difference scales with the number of inputs, and we normally have a few hundred inputs. Automatic differentiation is a relatively new technique. It's one of the main reasons why machine learning has been able to explode the way it has. And the idea is that whenever you write something in Python, eventually it gets compiled into instructions for the CPU, and those instructions contain a limited number of operations, of simpler operations. And we know the derivatives for all of those. We know the derivative of multiplication or addition. So when the compiler for Python is creating a computational graph to send to the CPU, it can also create a computational graph for the derivatives. So the cost of getting the gradients is about 2 times the cost of your original function. So it's extremely fast. And if you've been following the project, you know that we moved from MATLAB to Python a couple of years ago. And it was in order to take advantage of Python's automatic differentiation capabilities, which is like 100 times faster, at least. So that's all the background theory in very, very quick form. I'll say it took me, when I started this project, it took me a few months to really grasp all of it. So that was a very brief overview, but if you want to dig deeper and understand it, reach out to us and we can share papers and other resources. But I want to show a real quick case study for the WaveBot device shown here that we tested at the Mask Basin in Carter Rock. And we use a magnetic spring created by Portland State University that allowed us to change the spring stiffness and even create negative spring stiffness. And we were looking at the annual power production of the WaveBot. And this is the model for the WaveBot. In this study, we were looking at the drivetrain itself and the inertia in the drivetrain and the spring stiffness in the drivetrain, so KD and MD. And we were doing control co-design of these two parameters. And these were the results. Here on the x-axis, we had the drivetrain stiffness. The original device had 0 drivetrain stiffness. There was no spring in the drivetrain, as shown here in green, and had an inertia of 2 kilograms meter squared. And by doing control co-design, we found the optimal to be up here, which corresponds to a negative spring stiffness. And importantly, for every cell here, we find the optimal controller. So we're varying the physical parameters of our design, but at the same time, we are optimizing the controller for every design we consider. So this is a summary of the control co-design study. And the key finding is that a negative spring is optimal. And we went to Carter Rock and were able to verify that the optimal, the most power is produced when we have negative spring stiffness. And now I'll talk a little bit about WecOptTool. So how do you go about using WecOptTool to do a control co-design work? And I'll start by saying that WecOptTool is a Python library. So it's a collection of objects and functions that you can use in your workflow. It's not, let's say, a GUI with one single workflow you have to follow, or it doesn't have like an input file that you can then run on the command line. It's just a collection of functions and objects. And you really can create many different workflows using those. There's no one workflow you have to stick to. If you're familiar with codes like Captain, which we use in WecOptTool, it's the same thing. Captain provides you a bunch of functions and objects which you can use within your own workflow. So the way you would use WecOptTool is to start a Python script or a Python notebook and do all your work on that script or notebook using WecOptTool functions and then any other package you might want to use as well. And we have a few objects or variables you'll see over and over again, so it's good to familiarize yourself with. We have a variable we usually call Wec, which is a Wec object that's defined by WecOptTool. And it describes the equations of motions, so all your forces and inertial properties, as well as your constraints. And then we have the optimization state. We split it into two. XWEC describes the dynamic state, so the position of your device. Again, Fourier coefficients of your time trajectory. And XOpt is the optimization state for your controller or anything else you're optimizing. So XOpt is really free for you to play with. And then we have a waves variable, which is a data set containing spectral wave amplitude data. All functions in WecOptTool, when you want to use a WecOptTool function, have this signature where it takes the Wec object, the optimization state split up into dynamic and optimization, and the wave subject. So if you want to run a case, your own case in WecOptTool, you'd have to define these three elements. First is the Wec object. and that includes your frequency array. So the equivalent in like a time stepping scheme would be your time step, for example, how small your time step is. In the pseudospectral, you have to define some frequency array for your Fourier decomposition. And it also includes the BM coefficients, the hydrostatic stiffness, the inertia, any additional forces like friction or mooring or PTO, and so on. The waves, if you're familiar with X-array, it's just a data array of complex amplitudes indexed by the frequency, the direction, and the realization. For irregular waves, it's important to do many realizations of that irregular wave. It's more efficient than doing a very long simulation. So that's why we also have this realization index. And then you have to define your objective function. In the example today, we'll do electric power produced, but it can be anything. You could take it all the way to LCOE, for example, or it could be something completely different. But this is what you're optimizing, is your objective function. And once you define those three things, you call the solve method of the WEC object, and you pass it your waves, your objective function, how many states you have in your optimization vector, so how big your optimization vector is. The first part, the part that defines the dynamics, is fixed, but the second part is really up to the user. So the solver needs to know how many additional optimization states you're using, and then optional parameters for the solver. And in the tutorial today, we'll go through these steps exactly. We'll create a WEC object, we'll create a wave, and we'll create an objective function, and then we'll call the solve method. And I want to show that the code is on GitHub, Sandia Lab/WecOptTool. The source code is under WecOptTool. The pseudospectral solver and the WEC object are defined in core. Everything else are helper functions like PTO or waves. They help you create a PTO and a wave structure. But most of the core code is in this file, core.py. And in the repo, you also find the tutorials under examples. So we have 4 tutorials here. And I'll point out that on our website, which you can get through here, we also have sections on theory, how we implement this in Python, as well as the tutorials with the solutions already run, so you don't have to run the notebook yourself. You can read through it and see the results without having to run the notebook yourself. Yeah. So now we'll jump into the demo. So open CoCalc and open the file called demo.ipynotebook. And I'll give people a few minutes to do that.
I can also share screen and walk through getting into that environment if that's useful. I just put in the chat cocalc.com/project. And if you navigate to that, you should see a WPTO software demo days project after logging in. And then when navigating into that, there should be a directory named WecOptTool that has the materials inside of it.
If you want, you can share your screen, Dom, and show people how to do that. Right, and Kelly has her hand up.
Yeah, I just wanted to address the comment in the chat regarding starting CoCalc. In this instance, the user had 3 directories and did not have access to WecOptTool. Should be a button at the very top that says starting project or start project. If you hit that, the WecOptTool directory should appear and you should have the same view as Carlos.
Yeah, so
I had to refresh I had to refresh the browser after I started the project too. So if starting the project doesn't show it, click refresh.
I'll just share my screen really quick to demonstrate what I was mentioning. So if you follow that link, cocalc.com-project, and you log in, you will hopefully see, it'll say, just like this one says Megan Anderson, it'll say your name hyphen WPTO software demo days. When you click on that one, you'll hopefully, whoops, I was already clicked into the WecOptTools. Then once you click on that demo days, you'll see a couple options, and the WecOptTool directory will be in there. So when you click that, then which material was it, Carlos? Which folder is that's tutorial 1 WaveBot?
No, let's start with demo.
Demo, and there you go. So then demo.
All right, I'll share my screen again. And what do you think, Dom? Should I get started or give people another minute?
Yeah, maybe a little pause, but.
I'm still ready. Theory.
What was that, Daniel?
What's that, Daniel?
Maybe we can open the floor for some questions already while we wait.
Yeah, great idea. If anyone has any questions at this point before we start the demo, yeah.
I think whenever you're ready. Seems
Okay.
like everyone.
Yeah, I think things are going to become more clear when we do the demo. I know the theory is a bit difficult to grasp at first. For me, it was. So like I mentioned, WecOptTool is a Python library. So it just gives you a bunch of Python functions and objects. You have to use it within your own Python script. In this case, we're using a Jupyter notebook. And the first thing you have to do is we'll import WecOptTool if you want to use those functions. And we'll call it WOT for short. And then we import any other packages we might need for our own study. I would say you always do need AutoGrad. It's a wrapper on NumPy that does automatic differentiation. So instead of doing import NumPy, do import AutoGrad.numpy. And it has the same functionalities. You just use your code, type your code the way you normally do, but now any NumPy operation will be differentiable. So let's start by importing all our modules. And let's start with the waves because it's simpler. The WEC object is going to take us some steps to create. But in this case, we're going to do a regular wave. The first step is always to create our frequency array. And the way we define frequencies in WecOptTool is with a fundamental frequency and a number of frequencies. So F1 and N frequency. In this case, we'll do 0.3 hertz. This is hertz. And we'll do 10 frequencies. So just to show you what that looks like, if I do frequency F1, and this is what the array would look like. So 0, 0.3, 0.6, all the way to 3. But the way we define it in WecOptTool, we don't ask the user for a frequency array. We just ask them for the fundamental frequency and the number of frequencies. And then we define our wave structure. We'll do a regular wave. We'll use frequency of 0.3 hertz, which is our first frequency, and an amplitude of 0.1625 meters. For regular waves, if your problem is linear, you only need one frequency because all your responses are going to be at that same frequency. In this case, we'll do a nonlinear problem because we'll have constraints. And for regular waves, nonlinear problems, you want to include higher harmonics, and that's why we include several harmonics. For irregular wave, you want more fine discretization. You probably need more than 10 frequencies for a regular wave to represent the responses in irregular waves. And like I said, the waves is a data array of complex amplitudes, but we provide you functions on our sub packages, so WecOptTool.waves, to easily create them. So if you're creating a regular wave, you can just call the regular wave function in there. So let's run that, and let's take a quick look at what that looks like. If I look at what the wave structure we just created, you can see it's an X-array data array, and it's 3D. It's indexed by frequency omega, wave direction, and realization. And in this case, we're doing a regular wave, so there's no wave directions or realization, just 1 and 1. So it's really a vector of 10 in this case. And you can see that only the first entry has a complex amplitude because our wave is a regular wave at 0.3 hertz. So at that first frequency. So that all makes sense. You can create this from scratch, but there's no need. We provide you all these helper functions under waves. We have some for irregular wave, for directional waves. So you can take a look at that sub package. So we've created a wave in just a few lines. Now we'll create the WEC object. And this will take a few steps. But let's start with the BEM. We use Capitaine to obtain the BEM coefficients. That includes radiation, diffraction, Furt-Krylov, and Capitaine also provides us the inertia if it's a free-floating body, so it's a displaced mass, and the hydrostatic stiffness. And this is for simple cases. For more complex cases, you can overwrite that and provide the mass or inertia matrix yourself and the hydrostatic stiffness yourself. And these are all stored in one X-array that we typically call BEM data. So if you're familiar with Capitaine, the next few steps are going to look very familiar. We're not even using WecOptTool at this point. We'll start by creating, the first step is to create a mesh. For the wavebot, we provide that as an example. So we're just going to use that mesh. But in general, you'll have to create that mesh yourself, either programmatically in Python or loading an STL file or something else, any format that Capitaine can accept. And then we create a Capitaine floating body starting from a mesh. And just to give you an idea of what that looks like, let me do fb dot show matplotlib, and this is a Capitaine function. This is the top of the buoy. You can't really see the shape there, but you have an idea of what the mesh looks like in this case. And then continuing with the normal Capitaine workflow, we'll add degrees of freedom. In this case, we'll only simulate a heave degree of freedom. So only the buoy can only move up and down, just to keep it simple. And then we'll run Capitaine, and WecOptTool provides you this function called WecOptTool.runBEM, which really simplifies it. And Capitaine uses a coordinate system that's the opposite of the one we use in WecOptTool. So if you run it using our wrapper function, runBEM, it'll just give you the results in the right format and save you some steps. Capitaine has a lot of warning. Most of the time you can ignore those warnings. In tutorial 1, we talk further about what the warnings mean. So if you, after this demo, we recommend you actually go through tutorial 1 yourself. But now we've created the BM data with Capitaine. We can take a look at that. And it's a data set indexed by frequency and 2 degrees of freedom indexes and wave direction. we only have 1 degree of freedom in this case. But you can see we have added mass, radiation damping, diffraction for Krylov. Kapitchain even calculates inertia matrix and hydrostatic stiffness now. So we use those by default, but you can always overwrite them. Oh no, it froze. There we go. So again, we are creating a WEC object. We started with the BM that we need to create our dynamic equation. We'll now create a PTO, and we'll need a PTO for 2 different things. First one is to define an additional force in our dynamic equation. We want to have a PTO force. And the second is for defining our optimization objective function, which will be the average electrical power. And to make our lives easier, we'll use the PTO module to help us create this linear PTO. And one of the options to create a PTO in WecOptTool is to define as a 2-port impedance matrix. And I won't go into too much of the details of what this means, but I'll explain it briefly. A 2-port impedance for a PTO is this matrix here that relates the PTO force and the voltage of your generator to the velocity of your WEC and the current from the generator. So it relates your effort variables to your flow variables. And in this case, this includes the dynamics of our drivetrain, as well as the dynamics of the generator itself. And in this cell down here, we create this matrix. For those of you interested in how we model the PTO and how we model the generator, we have a few papers that explain it, and we're happy to share it. But I won't go into the details of the models themselves. But just from the inputs, you can see that we use some drivetrain variables like the inertia of the drivetrain, the stiffness in the drivetrain, as well as some generator variables like the winding resistance and winding inductance of the generator. So we can run this, and you can see we create this PTO impedance that has each of the 4 components. So these 4 components here. And even though I show it here as a matrix, this is a matrix for each frequency. So it's really 3D. So it's defined for every single frequency, in this case 10. So it's 2 by 2 by 10. Then we'll create a PTO object. This is also defined in WecOptTool. Unlike the WEC object, it's not required. You don't have to have a PTO object to run WecOptTool, but it makes calculating the forces and the power very easy, because all you have to do is provide this matrix, and then we have all the functions that help us create forces and power. We have to create the object. We need the PTO impedance we created, but we also need a few other things. The PTO number of degrees of freedom, in this case, it's just 1. There's only 1 PTO. Then a kinematics matrix, and what the kinematics matrix does is it converts from your WEC degrees of freedom to your PTO degrees of freedom. So let's say instead of a heave-only WEC, we allowed it to have planar motion, so 3 degrees of freedom. Then our kinematic matrix would be a 3-to-1, because there's 3 degrees of freedom in the WEC and only 1 degree of freedom in the PTO. But in this case, the WEC motion and the PTO motion are exactly the same. So it's just a number 1. The kinematics matrix, there's basically no kinematics matrix. And then the controller, we're gonna say no controller, which means find the optimal controller. What this really means is no structured controller. But if you want to put your own control design, like a PI controller, for example, this is where you will specify your own functions for the controller. So let's create a PTO object. And remember in the equations of motion how by default we include hydrostatics, excitation, radiation, and inertia, and anything else just to specify as additional forces. This is how you do it. You create a dictionary with a name for that force, and then a function representing that force. And I'll jump real quick back to the slides. Remember that all functions have this signature. They take in WEC, XWEC, XOPT, and waves. So what the PTO module really is giving you here, this PTO.force on WEC, is a function that takes those 4 inputs and give you the PTO force at every time step. And if you want any other additional forces, you can create them yourself in that same format, a function that takes those 4 inputs and outputs the force at every time step. So just big picture, we're trying to create this WEC object. We create the BM, the hydrostatic and inertia using Capitaine. Now we added the PTO force by defining a PTO impedance and using the PTO, WecOptTool PTO submodule to help us do this. And we defined our additional forces. The only additional forces we're going to include is the PTO. If we had mooring, for example, we can put mooring, or if we had other systems, we can include those forces here as well. And finally, we're going to start with no constraint. Later on, we'll add a constraint for the generator, a maximum force the generator can supply. But for now, we're going to have no constraint. So we run the cell. And we're finally ready to create our WEC object that defines the dynamic equation and constraints. So we do WecOptTool.WEC, and there's several ways of defining it. The most common and the one we highlighted today is starting from BEM, but there's many ways you can define a WEC in WecOptTool. And if we're using this from BEM, we need to give it the BEM data, any additional forces we want to add to our dynamics, and then any constraints. So everything we did before was just to get these 3 variables, BEM data, additional forces, constraints. And that defines our dynamics and our constraints on those dynamics. Cool. And then the last step, if you remember, let me go back to the slide. The last step, you have WEC object, waves object. We also have to create an objective function before we can solve. And the objective function is the thing we're optimizing. So we're designing our WEC and our controller to optimize something. And in this case, it's going to be power, electric power, which is voltage times current. And again, because we use the WecOptTool PTO module to help us, we don't have to write a function for average power itself. Just by giving it that PTO impedance, we provide you all the function to calculate this average power. But this is also a function of those 4 parameters. Remember, all functions in WecOptTool have that same function signature. And because we are using an unstructured controller, remember we have to specify the number of states ourselves. The unstructured controller we're using in this PTO object requires 2 times number of frequencies, just like it does for the dynamics. So what this 2 times number of frequencies is doing is it's the Fourier coefficients of our control trajectory. And in this case, the controller is the PTO force. So this is the, in this simple case, the controller is the PTO force. So this is really the Fourier coefficients of our PTO force. And finally, we're ready to solve. We call WEC.solve with the waves, the objective function. We have to tell how many states we're optimizing. And then there's a bunch of optional solver options. The ones that we almost always use are scaling. The WEC dynamics, so the position in meters, has very different magnitude than, say, the optimization, the PTO force, or the scale, the power produced, or the objective, I mean, the power produced. And optimizers don't do very well when the variables are very different magnitude. So it's helpful to scale them. So let's solve our problem. And it's solved in 13 iterations. And the optimal power per device is 197 watts. In WecOptTool, negative power means power taken out. So this is what we want. We want negative power, and we're minimizing this. So in this case, we're producing an average power of 197 watts electric power. And the optimizer uses, so I see there's a question. Let me finish this phrase real quick and I'll go to the question. We use SciPy for the optimizer. So the results that we get back are SciPy results. And we have some post-processing scripts to make it very easy to then work with the results. And that's it. In a few cells, we were able to solve a control co-design problem. There's a lot of understanding and learning. It's a bit of a learning curve, we'll admit. But once you know what you're doing, it's just a few cells of code and you can get the control co-design. And we'll go into the results after the question. I saw there's a hand up.
Yeah, that's I'm just raising the hand for the question in the chat. Someone says there's no controller. Does it mean that it uses complex conjugate controller?
Yes. Well, no. No controller means the trajectory of the controller is arbitrary. There's no structure to it. So the value at each time step is free for the optimizer to set. We don't look at the times values directly. We look at the Fourier coefficients, but basically each Fourier coefficient is completely arbitrary, and the optimizer can set it to wherever it wants to. There's no structure to follow. But in the case of the linear problem with no constraints, the optimal result will be the complex conjugate. But it won't use that. It won't use that knowledge. Especially later when we add constraints, the problem will no longer be linear, so you couldn't use the complex conjugate there. But that's a good question. So yeah, just in a few cells, we were able to get our results. But now let's take a look at them. So if you're familiar with X-arrays, they make plotting very easy. So let me show you something real quick. Code. In our post-processing, we created this PTO time domain array. If you look into it, it has position, velocity, acceleration, force, power, and then transducer flow and effort. In this case, is voltage and current of the generator. So the post-processing gives you all these variables for you to easily plot or use. And we have them for both the, you can see PTO time domain and PTO frequency domain, and WEC time domain and WEC frequency domain. So this post-processing function puts the results in a very nice format that you can use. So if we call PTO time domain force, and then we say plot that, we can see the PTO force on the WEC. And I'll say this 0 here, this is the realization. We're only using one realization, so just take the first one. But if you're doing irregular waves and you had many realizations, this index is where you choose which realization you want to look at. We can look at the power, the electric power. And finally, we also like looking at Sankey diagrams of the power flow. So the Sankey diagram shows you how much power goes into exciting the WEC. This is dark purple. And then how much is lost to radiation, or is radiated, and then how much is lost in PTO, in the PTO mechanical losses, and then how much is lost in the generator electrical losses, and finally your electric power. And in shaded here, we show what the optimal would have been if the device was well aligned all the way from geometry to controller, and all the impedances were matched. The highest excitation that could go into the WEC is this shaded part here. And if you know from linear theory of WECs, the optimal excitation, you have an equal amount radiated. So that's why this is here. But it's just a way of looking at the results that we find very helpful in designing WECs when we're using the control co-design approach. And then if someone has a question, feel free to interrupt, because the next step, we're going to ask you to try and add a constraint. So this was purely linear. Sorry, let me go back to the results. This was purely linear. We have a regular wave. Our dynamics was linear. We had no constraint. So the responses, like the PTO force, was also a regular sinusoidal at the same frequency. But now the power of WecOptTool, one of the good things is it's time domain. So we can do arbitrary nonlinear cases, and we can add constraints easily. That's something you can't do in other modeling tools. It's easily add a constraint. In this case, the constraint we want to do is say that there's a maximum torque our generator can provide, which translates to a maximum PTO force. So we want to constrain our maximum PTO force to 750 newtons. I should have written this here. Let me write it here. 750 newtons max PTO force. Something to note is that it's a symmetric constraint. And symmetric constraints, so it cannot provide more than 750 newtons on the upward direction, and it cannot provide more than 750 newtons in the negative direction. So plus and minus 750. And symmetric constraints can be written as a single constraint using the absolute value. So you have x has to be between negative k and positive k. You can write that as k minus the absolute of x has to be greater than or equal to 0. And this picture here illustrates that. Like I said, we use SciPy for the optimization, and their convention for inequality constraints is whatever function you give it, the outputs have to be greater than or equal to 0. That's the constraint. So we have to formulate our PTO force constraint like this: k minus absolute value of x, so that it's greater than 0. Greater than 0 means we're satisfying the constraint. And then for the SciPy optimization, you have to give it in a specific format. You have to say a dictionary that specifies what type of constraint is it, equality or inequality, and then give it a function for that constraint. And let me jump back to here. What we're asking you to do is to go to the constraint section, comment out constraints equals none, and uncomment the rest of it. So we have a maximum force that the generator can supply of 750 newtons. Let me quickly explain what n substeps is. In the pseudospectral method, we are enforcing the dynamic equations at a set of time steps, and only at those values determined by our frequency array. With constraints, we normally want to enforce them at even higher locations. So we might be enforcing, in this case, we're enforcing the dynamics at 10 locations, because remember we have 10 frequencies. So that translates to 20 time steps. But we want to enforce the constraint at 4 times that, so at 80 points. It just makes the pseudospectral method behave better. Don't worry too much about it. Just know it's a numerical thing. And the way we specify constraints in WecOptTool is you provide a list of constraints where each constraint is formulated in the format that SciPy optimize requires, which is this dictionary of type and function. So what we're asking you to do is to write this function for the PTO constraint. And remember, our functions in WecOptTool always takes its 4 inputs. In this case, it needs to return the constraint value at every time step. And maybe I'll pause for like 2 minutes to let you think about it. I don't expect you to actually get it on your first time using WecOptTool, but just 2 minutes for you to think about it, and then I'll walk through how we can do this. And again, if it's helpful, this is the constraint C that you should be outputting at every time step. It's this K minus absolute of X. All right, so let's walk through it. We're constraining the PTO force. So the first thing we should do is calculate what that force is. And if you remember, we used that already right here. So we know that our PTO object can give us that force directly. But this is a function. So let's call it with the current values. And that'll give us our current force. And then we want the thing that we want to be greater than or equal to 0, greater than or equal to 0, is our maximum force minus the absolute of our actual force. And we want this to be greater than or equal to 0 to satisfy our constraints. Remember, you can write asymmetric constraints as your limit minus the absolute of your actual value. It has to be greater than or equal to 0. And SciPy asks you for this this calculation that you want to constrain to being greater than or equal to 0. Now, the output of this force on WEC is not an array, it's a matrix, because in general, WecOptTool allows for many degrees of freedom. In this case, we only have 1 degree of freedom, so it is a vector, but it still has that dummy index for degrees of freedom. So to make it work, we need to flatten this matrix into a vector. So this is how you would do a force constraint. So now let's run it from here on. Again, great. Wait, what happened? Maybe I'll have to restart my kernel. I don't know why WecOptTool is no longer defined.
Just restarting and running all.
Yeah. Run all. So now you can see we produce less power because our generator cannot just provide any PTO force, it has a limit. So we're producing less power. Before it was, I believe, 197 watts. And this is our PTO force, and you can see it's limited at 750. And I'll talk about this wiggles. This is because we're using very few frequencies. We only have 10 frequencies. If we increase that to 20 or 30 and run it, it'll take a few minutes instead of a few seconds, but this will look pretty flat. And then our power is no longer a nice function like before. You can see all these nonlinearities because our force is nonlinear. So it works. We were able to model arbitrary constraints. In this case, just say our maximum PTO force is 750 newtons. And that's something that's very difficult to do in time marching. You kind of have to guess and try if you're doing a time marching scheme. And then we can look at our Sankey diagrams again.
Would you want to add the n substeps really quick in the constraint and show the effects of that?
Yeah, actually, you need more frequencies. I tried it both ways. Let me do that real quick.
I don't think you
So
do. Sorry.
okay. I thought I tried it yesterday and just more didn't work, but let's try it. So I could do, 10 substeps.
You didn't pass the n sub steps to the PTO force.
Oh, that would explain why it didn't work. Yes. There we go. And substeps. That's an optional input to PTO force. Oh, I didn't pass it in the beginning, so I never even used the 4. So 4 might be enough, actually. Good call, Daniel. Yeah, so 4 was enough. And it usually is. So this is where PTO force looks like. It's constrained at 750 and negative 750. And this is where our power looks like. And then I think we're a little bit ahead of schedule because I think they asked us for the last 30 minutes to be Q&A. So we're pretty close to schedule. I think we can finish it here and then just, Q&A. And our repo is on GitHub. We have an issues section where you can ask any questions you want. And then you can reach to me and Daniel by email too. And then we have like 30 minutes for Q&A and discussions.
Yeah, so we can open the floor. Thank you so much for the presentation.
Yeah, and I'll say in your CodeCalc, you also have tutorial 1 if you want to play with it without having to install Python and Captain and WecOptTool locally on your computer. But if you do want to do that, I would recommend you do. You have all 4 tutorials on our GitHub. But for a quick, like checking out the full tutorial 1, you can keep using CodeCalc.
So any questions on the demonstration? If not, I can kick us off. I'm curious, what's the how does WecOptTool fit like kind of in the ecosystem of other WEC modeling tools? Like I am a novice at this. What is the like the advantages and disadvantages and how it kind of fits in and it helps out?
Yeah, that's a good question. Many of the existing tools are good for evaluating the performance at one design, for a given design. WecOptTool is really an optimization tool. So if you want to optimize some physical design element like your spring stiffness or the gear ratio or your geometry, and at the same time optimize the controller. So for example, if you're using something like WecSim, you have a specific WEC and you have a specific control, you can simulate that. But if you want to try a different control, you have to run another simulation. Or if you want to try a different geometry or a different gear ratio, you have to run a new simulation. And the optimization is not done automatically. Here, the optimization is done automatically. So you can find your optimal controller in a single solve. You don't have to keep iterating. In a single solve, you can of WecOptTool, you can find your optimal controller. Constraints is another one that's very difficult to enforce in time marching schemes. So if, for example, our PTO force not being more than 750, or a constraint of like the position not exceeding some value, that's it's not straightforward to enforce in time marching schemes. So it's really an optimization tool for initial design exploration, is what I would say. When you're still playing around with your design and trying to design the WEC itself. Once you have a more finalized design, you can go to higher fidelity tools and time marching methods and so on. Did I miss anything, Daniel, and how this fits into the bigger picture? We'll add some stuff.
Yeah, I think that's great. I think we could comment on limitations. Like WecOptTool is not really meant to communicate with hardware or real-time systems. So there, the functionality of Simulink that you have is invaluable, but WecOptTool could inform the control design, and then you could use real-time tools to test those controllers on hardware, for example.
That's really interesting. Thank you.
And I will say that WecOptTool is very powerful when we're using the optimal controller, because it helps us find the physical design that with a good controller will produce the most energy. But in reality, you'll never be able to implement the optimal controller. That gives you kind of like a top cap, but it's a very powerful design tool, because we end up designing the physical device that theoretically could give us the most power if we have a good controller for it.
Interesting. Any other questions? If not, what other tools, or what other efforts have used WecOptTool, or is there a way to use experimental data? Oh, there's one. That's a question. Sensitivity analysis. I'll comment more.
Yeah, to the sensitivity analysis in the chat. Basically, one of the first examples Carlos showed, where we looked at the optimal PTO for the wavebot as a function of drivetrain stiffness and drivetrain inertia and controller. We could have formulated a problem so that we only find numeric value for the optimal drivetrain inertia and the drivetrain stiffness and controller. But the problem was formulated so that we kind of like have a discrete sweep over different values that we think. So we can see here from this plot how sensitive average electrical power is to those different input variables, like the direction of the average power gradient. We can see this is a feature that you can implement with WecOptTool, where you just learn a lot from looking at the trends in your objective, in this case, average electrical power.
Yeah, and to be clear, you can run WecOptTool in a way where it just converges to this orange box, and it just gives you that final solution. In this case, we can split it up and run a bunch of cases to see the sensitivity. And in each of these cases, it finds the optimal controller for that design, for that drivetrain stiffness and inertia. But we could have included stiffness and inertia in our optimization, and the optimizer in a single solve could have given us this value. But we often find it more productive, like Daniel said, more useful to do a bunch of simulations instead of just one and actually see the trends.
It looks helpful for building intuition. Nice. So how would you use experimental data with WecOptTool?
I'll let Daniel talk about it a little bit more, but I'll say first that we've used WecOptTool to inform experiments. So, for example, we did a lot of WecOptTool simulations when we were doing the mask testing of the WecOptTool, and we saw similar trends with negative stiffness being optimal, for example. So this informs like what do we want to test, what do we want to look at more deeply, and then we've also been able to use the experimental results to create models for the WEC. So in the code, if you remember, when we created our WEC object, we call a function as from BEM. What we've done is create the WEC object with an intrinsic impedance matrix created from the data. from system identification of experimental data. So in that case, we don't need Kapitein. We don't even run Kapitein. We don't need BM coefficients. We just create a model, a linear model from the data through system identification from the experimental data. And then Daniel has done some work with the nonlinear generators. If you want to talk about that, Daniel.
Yeah, if you are interested to go beyond tutorial 1, tutorial 2 looks into that. The PTO function, as Carlos introduced, it would take more arguments, like loss would be another argument. And this is what Carlos was referencing to. We have used the two-dimensional efficiency map of generators that are a function of the torque and the instantaneous current they apply. And you could also take that into consideration in your PTO, and so that it will calculate, it will take the generator's efficiency into account before calculating the average power, and then find the optimal trajectory, how to move in that generator efficiency space in combination with the hydrodynamics and the PTO dynamics. So I guess to come back to your initial question, how can experimental data be used? There's really no straightforward answer, because it could be at any stage of the models, or at none, or at all. Like you could equally, Carlos has opened the drivetrain impedances. If you do have a test bench to identify your drivetrain dynamics, you can also replace that with an empirical function.
Yeah, so the core WecOptTool is just a pseudo-spectral solver. The models that you use to define your dynamic equation are really arbitrary. We give you a few ways to make that easy. Like if you have BM data, we'll calculate those forces for you. But you can replace any part of the dynamics calculation or the objective function with models derived from data. In this case, we're modeling the PTO and the generator as a linear system using linear models. This is something Daniel has replaced some parts of it with data from actual generators that have like nonlinear maps based on data.
Wow.
I have a question. You guys hear me?
Yep.
Okay. Can you add cost as a variable in the objective function?
Cost can be your objective function, yes. Your objective function is usually a single value. In this case, it's electric power, electric average power. It could be cost, yes. We don't have any functions pre-populated for users that calculates cost, because that's very case dependent. Yeah, you can create your own function that takes in the WEC position, the controller, the waves, and gives you the cost. And we should do an example like that. It shouldn't be too difficult, but we haven't. We've been working with power mostly. But your cost function can be anything. It could be, I want to minimize the tension on a line or something.
Just add to that, as Carlos said, the numeric aspects are not difficult to add the cost. I think creating a meaningful optimization problem is the more challenging part. So, if you want to get to an LCOE proxy, for the optimization to be useful, you need to know how does my drivetrain inertia change the final cost, and then you can find an optimum. But I think this is that modeling aspect. Like, how do my hull shape, drivetrain parameters, whatever, how do they actually impact dollar? Modeling that is more difficult than formulating the optimization problem.
Got it. Thank you.
Oh, wow, that's really interesting. Thank you so much. If there are no other questions, I guess leave the floor open a little bit longer, and then might
I have
close
one
this
more.
out.
Could you talk a bit about getting into multiple bodies and joints, connecting those bodies?
Yes, and we've done a few examples with those. WecOptTool can handle multi-degree of freedom on both the WEC dynamics and the PTO. So you can have, for example, a 5 degree of system, degrees of freedom WEC, like the FOSS-WEC, if you're familiar. It's a floating platform with 2 flaps. That's 5 degrees of freedom, and then there's 2 PTOs that are rotational, so that's 2 PTO degrees of freedom. And basically everything instead of a vector of time series, it will be a matrix where every row is a time series for each degree of freedom. So your position will be a matrix of 5 times number of time steps. Your forces will be 5 times number of time steps. You have to write the dynamic equations following that same format. If your dynamics equations are just a simple linear case that we use here, it works nicely. If it's more complicated, it might require some effort on your side. But no, it works. It works well with multi-degrees of freedom. I would say the optimization sometimes can be a bit tricky to get it to converge. So with multiple degrees of freedom, you might have to play a little bit with those scaling factors to get it to converge. But no, in general, we can handle multi degrees of freedom and joints. The joint will be reflected in your dynamic equations or your constraints. And if you're using our PTO module, there's a kinematic matrix you can define that translates forces from the WEC degrees of freedom to the PTO degrees of freedom. And I believe one of our tutorials does one of the tutorial have multi-body, Daniel?
The LUPA, that's Oregon State's signature wave tank project that has multiple degrees of freedom, yes.
Yeah, so that's a good one to look at for that. Anything else on multi degrees of freedom and joints, Daniel, that I'm missing?
There is the other tutorial for that models a non-hydrodynamic body that is connected to a hydrodynamic body. That's a pitch resonator. Also an interesting example to look at.
And one last thing is that we use a Capitaine, so we can handle arbitrary general degrees of freedom. So for example, the FOSS-WEC can be modeled as 5 degrees of freedom, as opposed to 3 degrees of freedom for each body plus constraints. Both are possible in WecOptTool. It just depends on how you formulate your equation of motions and how you run your PM.
Well, if there are no other questions, I'll close out.
I'll say one last thing. We recently became a teamer facility, so there's opportunities to work with others to use this tool. And if anyone's interested in using this tool for their projects, we are always willing to meet and help you get started. Yeah.
Great. It's always good to keep that in mind. The whole point of this is to have discussion and collaboration. So reaching out, never a bad thing. Share my screen. So just a quick reminder that the next session for the demonstration days is the finale. We'll be talking about primer and also having a bit of a recap for the sessions that we were able to cover over this series, and that will be on July 2nd. Yeah, and if there are no other questions for the presenters or demonstration days at all, thank you so much to Carlos and the team for presenting on WecOptTool. And thank you everybody for attending.